Alright, so methane. Carbon has 4 electron dots. 1, 2, 3, 4. You can put in your lab notebook because we're going to continue this whole process here in a minute. So here's carbon, starting on the left here in this row, 1, 2, 3, 4, 2 s electrons in the valence level, 2 p electrons in the valence level. So there's 4 electron dots for carbon. Hydrogen has 1 electron dot. Okay, and what I want to do is arrange these so that the hydrogens have 2 electrons and the carbon has 4. So if I share these 2, and these 2, and these 2, and these 2, then the carbon has 8 electrons then and a full valence level. The hydrogens all have 2 and a full valence level. And then I squeeze the electrons between the atom symbols, and you get this. So now how many round balloons do we need? None. How many long balloons do we need? 4. We need to try to arrange those so they have that tetrahedral arrangement. So if you recall, when we're doing stick drawings for this, a set of electrons would go up here, a set of electrons would go down here, a set would come out towards you, and one would go behind the board. Okay? And then we would have put the hydrogens on those. So this is a structural drawing for methane. When we do the balloons, they're going to have those same angles. And that's the whole idea behind doing the balloons, that you can see that. These pairs of electrons don't like to be near each other. Right? I can put 2 electrons near each other in the same orbital because they're quantumly entangled. Or you could say they also have opposite spins. It cancels the electromagnetic repulsion. So I get 2 of them together in the same orbital space. In this case, it's a hybrid set of orbitals. But once I get the 2 together, they're not going to want to be close to the others because of the opposite spin. I can only cancel the electromagnetic repulsion one time with opposite spins. So this set wants to be as far apart from that set, and that wants to be as far as they can from this set, and so forth. So that all of these now have an angle of 109.5 degrees. Okay? And when we do the balloons then, we're going to have a central nucleus here. I'm just going to put C for the center of the carbon. And I need a long balloon-shaped orbital. This is called a sigma bond that goes vertical. So this is sigma. Now it's coming from an sp3 hybridized carbon. This arrangement right here comes from sp3 hybridization. Okay? Remember our balloons when we did sp3 hybrids? Okay, we had 4 balloons pretty much arranged like this. So this is still sp3 hybridization. And then I've got an orbital that is shared, forming a sigma bond that's coming out like this. And there's the hydrogen on the end. I didn't draw that before. When we did the balloons themselves, we actually made a little tiny balloon thing on the end that would have been where hydrogen goes. This is still sigma, but it's a shared orbital between the hydrogen and the carbon, and the orbital from the carbon has an sp3 hybridization. And this is hydrogen, and this is hydrogen. Now I need an orbital that's going to swing out toward us. And there's a hydrogen on the end of this thing. Okay? So those of you who've taken art before, you know what perspective is. What I'm trying to kind of show here. This orbital was an sp3. It's hybridized to an sp3. But since we're sharing an electron in this orbital, and we're sharing the orbital itself, we've got a sigma bond. A sigma bond is any bond that lies directly on the line between the nucleus of 2 atoms. In this case, the hydrogen and the carbon. Okay? And then finally, we're going to have a shared orbital forming this sigma bond that's going to come out behind everything back here. Okay? And a hydrogen on the end. So here's the hydrogen. This is the sigma bond here. And I'll just have to draw an arrow to show where the sp3 goes right down there. Okay? So if we were going to make a methane molecule, we just make 1, 2, 3, 4 of these things like we did with the water. Okay? And tie them all together really tight, and I'll make that same shape, that tetrahedral shape. Does that make sense to everybody?
Is that what we're doing?
No.
Okay.
We're going to move on to double bonding today. Okay? Y'all with me so far? Can you see this in your head? Can you see the three-dimensional structure in your head? And we did 2 of them. We did hydrogen chloride, and we did water. Okay, can this make sense to you? The idea is that these drawings start to allow you to see a movie in your head, and you can make predictions about shapes without having to actually make the shapes themselves. Okay? All right then. So, time to go to double bonds. You ready to go to double bonds? Now, this is still going to go in your lab notebook because it's part of the lab.